So let me begin with the following problem that we discussed on the previous lecture during the previous classes. Let me assume that I have a coin, and I toss this coin, for example, toss a coin 5 times, and I have 3. Okay, not 5 times, but for example, 10 times. And I have 3 heads out of these 10 tossings. And my coin have some probability that it yields head. So we have some probability that we have a head in one tossing. And this probability equals to some parameter of my model. Let me denote this parameter by theta. So my first question is the following. What is your estimate for theta? How do you estimate theta in this case? So you can just provide your answers. Okay, you can think about this problem a little bit, and I need to find one thing. And just in a second, I will return. So there is a question. Do you have to recall the formula for confidence interval? No, I just want your point estimate, just one value, one number. How can you estimate from this data? So you have some data, this 3 out of 10. And how can you estimate from this data this value of theta?
We use maximum likelihood estimation, and our best estimate here is 0.3.
Okay, so your best estimate is maximum likelihood estimate. And as we discussed on the previous lecture, in this model, if we use binomial random variable to estimate its parameter theta, probability of success, we can just divide this number by this number. And so this is 3/10, this is 0.3. Okay, everybody agree? O.3 is your estimate, your guess, right?
I think everybody agree.
Okay, at least nobody objects. Okay, then let us repeat this experiment. This is a coin. It is 2 € coin. I don't know why. This is just a random coin that I get from my backpack. And let us do this experiment. So you can see this coin. This is just an ordinary coin, I believe, but probably not. And I will toss this coin once. So yeah, I tossed this coin and I have head. I'm not sure that it is clearly visible with my camera, but it is in fact head. And so this is the result of my experiment. We see that we have a random tossing again. We have one tossing. So one tossing. And we have x equals to 1. So one tail, one head. And again, let me ask you, what is your best guess for this coin? What is your best guess about the parameter of this coin, about the probability that this particular coin that I used gives you so what is the probability? What is the probability of obtaining head for this coin? Can you give me some estimate using all the knowledge you have so far? Any ideas?
Isn't it just one?
So, you guess about theta, that theta equals to 1. So it means that we have a coin. So you believe that this coin yields head every time I toss it. 0.5. So we have another option that this is 0.5. Some other options. Okay. So it should be polling somewhere in this interface, but I don't see it now. Okay. So
Maybe it's between 0.5 and 1.
somewhere in between.
Yeah.
Somewhere in between. Okay, so we have three options so far. 0.5, 1, and somewhere in between. Who indeed believes that the answer for my actual coin, that the answer is this one, that theta equals to 1. So let us make a vote. Who is just write into the chat who is in favor of which option about this particular coin. Just what do you believe in? This is a practical question. This is not some abstract scientific things. This is just an actual coin in my hand. Okay. So 1, other options. Okay. Okay. So I need more answers. Yes. Mm-hmm. Mm-hmm. So initially it was a group of people who believe in 1, and now we have a group of people who believe in 0.5. So who wins? Now the score is 3 versus 4. So every vote can be concluding. One. So nobody in the party somewhere in between. Nobody believes that this is a special coin that toss that in one tossing yields a head with probability in between.
You
Something.
shouldn't have said us that you have chosen this coin randomly.
Okay, this is a coin from my backpack. This is everything that I can tell you about it. So far we have a tie. Half of you believe in 1 and half of you believe in 0.5. Okay, but do you really believe that I created a special coin that looks like an ordinary 2 eurocent coin, and just to show you this experiment? Okay, so if you don't actually believe in it, why don't you? Why do you say that your best guess about theta is 1? To say that your best guess about theta is 1 is just to say that you really believe that this coin is such a special coin. I don't know. I heard some stories about people in prisons who can create such coins for some gambling purposes, or I don't know. But basically, what is your belief that I can produce this coin? Actually, it is possible. Yes, probably I bought this coin especially to troll people at probability theory classes. But if we use the knowledge about everything that we know, not only about some statistics, but about some real life, then what can you say about probability that this coin is such a special coin that produce heads with probability 1? Have you ever met in your life with a coin that looks like a normal coin, but produce heads with for probability 1? I think neither of you met with this kind of coins, and actually me neither.
We didn't check all of them. We can't say.
Well, at least I didn't ever figured out that I have such a coin. So basically, this story is about our estimates and about our beliefs about our priors. So we have some. Previously, it was like ordinary conversation without any huge scientific terms, but we can translate it into scientific language. So first of all, if we are interested in maximum likelihood estimate, then indeed this answer is correct, maximum likelihood estimate for our experiment. So in fact, theta maximum likelihood is 1. But if we plug some common sense into this problem, we see that even despite the fact that this is maximum likelihood estimate, we cannot actually say that we believe in this estimate. Why? Because we know that it is virtually impossible to get this kind of coin. That if indeed I just picked this coin from my backpack, as I said, and if I'm not a specialist in some visual magic, then most probably this coin is just an ordinary coin, like all of us have in our pockets. So it can be said that we have some prior. Before I did an experiment, before I tossed this coin, you had some prior, some belief about what kind of coin it can be. And when I ask you this question, do you really believe that this coin is like this one? Do you really believe in this estimate? You plugged these prior beliefs into your estimate and said no. Don't actually. Why? Because your prior probabilities, your prior beliefs about this coin were against this idea, too strong. Okay, let me open the cards. This is just an ordinary coin. And for this coin, theta equals to 1/2. And this is not a surprise, I think. But if, on the other hand, assume that I did a similar experiment probably with other coin, and assume that I have something like n equals to 100 and x equals to 100. What is your best estimate for theta now, if you imagine this experiment?
1 again.
Now it is probably it is 1. So you see that these results are much more provide much better evidence for this estimate. This is, in a sense, it is in some sense it is similar to a story about hypothesis testing, but in contrast with the story about confidence about hypothesis testing, I didn't stated any null hypothesis at the beginning. I just said, we have data, give me an estimate. I didn't ask a question that can be answered like yes or no. I didn't ask a question, is this coin fair or not? I just asked a different question, a question of estimation. So we see that in this estimation problem, we can obtain different results. And sometimes these results are close to our maximum likelihood estimate, and sometimes not. Like here, we do not believe in this maximum likelihood estimate because this estimate contradicts to our prior knowledge, to our beliefs. Let me consider another experiment. Assume, for example, that we have n equals to 5 and x equals to 5. What is your estimate now? Assume that you have three options. Theta can be either 0.5 or 1, or it can be or it can be something in between. So if we have these results, we have 5 tossings and 5 heads. What are your best guess now, just from intuitive point of view? Any guesses? Something in between. So 1. It feels like we need more testing. Sure, we need more testing, but we don't assume that we don't have ability to get more data. Of course, more data is better than less data, but assume that you have to provide some good estimate now with this data. So. So, Irina, do you strongly believe in 0.5, even despite the fact that we have 5 heads out of 5 tossings? Okay, what if I increase number here? Like, what if I add 1 here? Again, note that I said that I don't have special coins, but probably it is possible that somebody have. Okay. So we see that if I increase, number of tossings, number of trials, then at least some people shifts from this estimate to this estimate, and somebody shifts to this kind of result. Actually, I wonder why this option is so unpopular, because actually, if we see this result, and on one hand, we have strong feeling that there are no the coin with theta that is not equal to 0.5. But also we have strong evidence in favor of this result. So probably the truth is somewhere in between. Okay. Now it was some discussion about our intuition. Now let us provide some rigorous model for this discussion. We have Bayesian model. Let me recall that previously we considered this value theta as something fixed, something that you don't know, but something that is fixed. This coin can be either fair or not fair. And this is some reality that is fixed. But from Bayesian perspective, more or less everything is something random. Your parameters are random. So in Bayesian model, we have something like this. We have theta, our parameter of our model, is random variable. And then we have n, number of tossings. Let us assume that it is some fixed number. And then we have x, number of heads. And we believe that this x is binomial random variable with parameters n and theta. So this is just a formalization. We say that x is number of heads when we tossed n times a coin, such that probability of one head is theta. I need to impose some distribution about this theta. This distribution is called prior. Let us consider some prior. Actually, theta is probability, so it can take any possible values from 0 to 1. But for simplicity, let us consider now some prior distribution which is not continuous, but just discrete. Let us assume that we have only several possible values of theta. Let us consider, for example, that theta can be either 0.5. So we have theta and we have probability. And let us assume that theta can be either 0.5 or 1. Which probabilities will we put here? What is our belief that probability that theta equals to 0.5? What is the probability that I want to put here? Before we ever tossed, I just have some random coin. Okay, let me use different coin. This is 1 euro cent coin. This is different from the previous one. What is your belief before I did any testings with this coin? What is your belief that this coin provides yields heads with probability 0.5?
1.
1. Okay, it will be not very interesting model. Let us assume, let us give us some probability that I bought this coin from some person who do some magical tricks. And let us put some probabilities. Of course, we will put here much larger probability than here, but let us put here probability 0.9 and here probability 0.1. So I can say that probability that theta equals to 0.5 is 0.9 and probability that theta equals to 1 is 0.1. And there are no other options. This is actually one of the possible distributions, and I just let us just consider this distribution just to proceed. We can consider different distributions as well. Now, assume that we performed our experiment. Again, for simplicity, let us assume that n equals to 1 and x that we observed is equals to 1. Now, I can ask you, what is the probability that theta equals to 0.5? Let me write it as a conditional probability. Actually, what is the difference between this probability and this probability? This is a prior probability. This we believe in this estimate before we seen any data, and this is our posterior probability. So this is called prior. And this thing is posterior. Because in this case, we assume that we seen the data and the data is this one. So who knows how to find this probability? I think everybody should know because I believe I have a strong prior and that it was discussed on the course of mathematics with Nina. So who remembers how to find this thing? Did you discuss Bayes rule at mathematics? Okay, look, this is a simple question, and you can answer either yes or no. So this is not a question about some estimation. Did you remember anything about Bayes rule? Okay, yes. So, okay, so do you remember anything? Multiply probabilities. Which probabilities? Okay, let me draw a picture. We assume that we have a two-stage model. At the first stage, we select theta. And this theta is selected according to this distribution. So basically, it means that I believe that I have a lot of coins in my backpack, and most of these coins, actually 90% of these coins are just ordinary coins, but 10% of these coins are these two-head coins that yield head with probability 1. So first I collect a random coin from my backpack, and then I toss this coin once. And the result is this random variable. So let me draw the following scheme. First, I select theta. And this can be either with probability 0.9 theta equals to 0.5, and with probability 0.1 theta equals to 1. Then I toss a coin. I have the second step. And then I can either get x equals to 1 or x equals to 0. So if I have theta equals to 0.5, under this condition, what is probability that x equals to 1? What should I write on this arrow?
(0.5).
Correct. So we have probability 0.5 here and 0.5 here. And what about these two arrows?
1 and 0.
1 and 0, correct. Now we see that x equals to 1. So we know that we are either here or here. What we are interested in is theta. We are interested in possible value of theta. Of course, theta can be this and theta can be this. So both options are possible because in both of cases we can just get to this value. But we are interested in new posterior probabilities of this theta. So we are here or here. This is our observation. We don't know here or here, but we know that x equals to 1. So what should we do? To find probability that theta equals to 0.5, provided that x equals to 1, we have to, actually, it means that we are interested in this outcome. What is the probability of this outcome? So we have probability. So what is the probability to get here? To get here, we have to select correct theta, and then we have to get a correct result here. So what is the probability to get this result, to be in this point? How did you find this number, 0.45? How did you find it, Irina? So I believe that you multiplied 0.9 times 0.5, and it is 0.45. And now, what about this? What about this path? 0.1. Now we have two alternatives, and we can be either here or here. And we understand that we have to be either here or here, no other options possible. And we see that probabilities of these events, just without any conditions, unconditional probabilities of these events, are shown here. So to find the conditional probability, we just have to divide this value by the sum of these values. So this is probability that theta equals to times probability that x equals 1, provided that theta equals to 0.5, divided by probability of x equals to 1. So this is Bayes' rule. So we are interested in this conditional probability when theta is 0.5 under condition that x equals to 1. But initially you have different conditional probabilities. You have conditional probability that x equals to 1 provided that theta equals to 0.5. So they are different in their meaning. And to find this thing, you have to multiply this conditional probability by this prior and divide it to this probability. This division is actually a kind of normalization. We have two possible alternatives. What is the probability of this thing? How to find this probability? In our model, theta can be either this or this. Theta can take value either 0.5 or 1. Assume that we observe that x equals to 1. And we found probability that theta equals to 0.5 under this condition. What can I say about this probability? How can you find it? Okay, you have two events, and exactly one of them will happen. What can you say about their probabilities? Can anybody answer this question? Mhm. So, Лиза, what is это у вас ответ на какой вопрос?
No, we should now we can think that the probability of getting one is one, as we have only one toss result. So we have one in the left side. We know probability of 0 x equal to 1. It is the sum of probabilities of possible options, and we know the probability of the second probability in числителе. So we can count the probability we are interested in, the probability of theta is equal 0.5.
Okay, so I'm just not sure about division on 0.5 because actually this thing can be found by in this formula. You cannot just replace this thing with 1. It is incorrect. You have to find this probability using actually just by a summation of this value and this value. So in this case, this calculation will be like this one. So this is just okay. We can find the numeric value. I will use some calculator to find it. So it is 0.82 approximately. And if you know that this is 0.82, what can this value? If you know that this value is 0.82, what can you say about this value? Yes, we can just subtract. We know that the sum of these values, of this value and this value, should be 1, because according to our model, theta should be either order 5 or 1. So we can assume that their sum equals to 1. So we can use this to find probability. On the other hand, the same thing can be done by using a formula. I just have to replace in fact, I just have to replace this and this value. This is probability that theta equals to 1 prior probability times probability to get our data provided, that parameter equals to this value, and divide by probability that x equals to 1. So I can just use this formula.
Does the value 0.82 depend on the probabilities 0.9, which we have chosen before doing all
Sure.
this
Yes.
calculation?
Yes. They depend, and this is very important. Actually, you see in our calculations that we use these numbers. And in fact, if we change these priors, then we will get results here. Actually, this bias rule connects 3 things. We have some prior. This is our info about the world that we know before we seen any data. Before we data. Data. And then we can we use both of them to create a posterior. This is our beliefs, our updated beliefs. We observe data. So this is the core idea of Bayesian inference, that you have some information, if you have some beliefs about the real world, then that you had even before you've seen any data. Then you have some data, and then you update your beliefs about the world just by combining data and prior. Actually, in this case, you see.
And if we do one more iteration without new data, just put 0.82, we will update it again, or we will get 0.82?
How do you want to update your beliefs without data? In this case, data value. Without data, you cannot. I don't know. How do you want to proceed? Как действовать без данных?
Если мы затем возьмем то, что получили, и подставим изначально, мы будем до бесконечности обновлять или на первой итерации завершим?
Я понял. А данные вы хотите взять те же самые, что были?
Да.
Я понял. Да, okay, I see. So the idea is just to update beliefs and then just use the same data to update these beliefs once again and once again and once again. Yes, this is not correct approach, because this approach is actually equivalent to if you will proceed in this way, actually will get you actually will get this estimate. So to do what you said is just like, imagine we have not only this one experiment, but that we have result of infinity number of similar experiments, and all of them like this. And in this case, you will get the result that if you proceed more and more times, you will get results that are close to here. But this is not correct way to do Bayesian statistics. The correct way is just to use data once, to update your beliefs once. Let us look at this example once more. You see that initially we have a probability 0.9 that our coin is just a number. After we saw this value x that is equals to 1, we updated our belief. And now our belief is this one, 0.82. So we see that this result provided some evidence in favor of this value of theta. Yes, in favor of this value of theta. So this result increases probability that theta equals to 1. But still, even despite see this x equals to 1, we still believe in this option with much more confidence than we believe in this option. We still think that probability is rather large, but a bit smaller than it was before we see the data, because our data are in favor of biasness of this coin like this. So I don't know actually. Are there any questions about it? Let me read terminology that we used previously. Previously, we said that we have some parameter of the model, it is theta, and we have some data. And how did we call this conditional probability? How did we call probability to get the data that we obtained with a particular value of parameter? Do you remember from the picture? In this case, it is in fact conditional probability, but we used some special name for probability to get the data that we have, provided that we fixed some parameter of the model. No, it is not posterior. Posterior is a probability to get some particular value of theta. How would you call this thing? In fact, this thing is called likelihood. And this is value of likelihood at some particular point theta. So we have the following. We can rewrite this formula in the following way, a bit more generally. That I want to find probability of theta for a particular data. And this probability equals to prior probability of theta times likelihood of theta. Divided by probability to get data. This likelihood, in fact, depends on data as well. Let me put it here. And this thing does not depend on theta. It is just a constant. So this is a general formula for Bayes rule. Now let us consider a little more complex example when we have more complex distribution on this theta. So previously in our prior, we assumed that theta can take only two possible values, 0.5 and 1. Now I want my theta to take any possible value from 0 to 1. So assume that I have some distribution for theta. And let me assume that this distribution is given by some probability density function. Something like this. So this probability density function take non-zero values only for values from 0 to 1. Something like this. So this is prior probability density function for theta. So before I see any data, I believe that theta is randomly selected from a segment from 1 to 0 with this probability. Okay, we can consider some more or less linguistic data. Let us assume, for example, that we have several informants. Okay, let us assume that we have one informant. And this informant produced some text, and we count again. We count some realizations of some linguistic feature that can be in one or another state. For example, dialectical and not dialectical. Assume that we have one informant, and this informant assume that it produced that this informant that he or she produced n equals to like 10 words, and out of these words we have 7 dialectal. And what we are interested in is probability to get dialectal world. So this is theta. This is exactly the model that we discussed so far. We can model our informant as a person with some coin, and every time they have to produce a word when they choose between dialectal and non-dialectal realizations, they just toss this coin once. And we have some probability for this particular person to get a dialectal word, and this probability is a parameter of our model. This is our theta. And we also probably have some statistics about other informants, about our population. And we believe that our thetas are distributed according, for example, to this law. So we see that half more than half of people will produce dialectal word with probability less than 1/2. And we have some other part who produce them more often. But also we see that there are almost no people who do not produce them at all. So we have this kind of distribution. And we believe that our informant is taken from this population. So the prior probability of this theta is like this. And then this is our prior. And then we do our experiment and we get our data. Then I can ask you a question. How can we update distribution of theta? So I want to find posterior distribution of theta. In this case, I do not use probability because my theta is a random variable. So instead I will use probability density function. So I'm interested in probability density function of provided that x equals to 7 and n equals to 10. To find this probability density function, I have to do the following thing. I have to multiply. Again, I have to multiply prior probability so prior PDF for theta. Let me denote it PDF prior of theta times likelihood. Likelihood of theta and divide everything by probability, or in this case, okay, yes, this is probability to get our data. Let us, how do you think, how the graph for likelihood looks like for these values? Actually, this is binomial random variable, and we can find this likelihood. This likelihood is probability to get 7 successes out of 10 for some probability of success theta. So do you remember the formula? What is the probability to get 7 heads out of 10 tossings provided that the probability of getting one hat is theta. Do you remember the formula? Okay, we will recall the formula later, but now let me just draw the corresponding graph. So I have likelihood. Okay, theta times 0.7. No, this is incorrect. Okay, let me ask a different question. What can you say about the value of theta that provides maximum for this function? Where maximum of this function is attained?
It's 0.7.
Yes, exactly. This is actually our maximum likelihood estimate. So we can assume that this graph looks like the following, something like this. We will have 0 here and here, and maximum here, and something in between at the rest. So to find our posterior, we have to multiply this graph by this graph. So let me draw both graphs on the same axis. So I have this graph. This is my prior. And I have another graph. This is my likelihood. Probably I have to rescale them, but it is not important now. Then I have to multiply at each point. I have to multiply the corresponding values. And what will I get? In these points, we have large values of our prior. So this is prior. At these points, we have large values of prior, but low value of likelihood. So our data provides evidence in favor of these values of parameter. But this vice versa. Our prior provides some our belief that we can get a value of theta here, but our data does not support it. And here it is vice versa. Here we have prior, but large likelihood. So when we multiply them, they will, in a sense, cancel each other. Not directly cancel, but we will get rather small values here and rather small values here. But somewhere in between, it is possible to get much larger values of posterior probability. So our posterior can look like something like this. Something in between. For example, let us assume that here we have 0.2 and here we have 0.4. So this is our posterior. What does it mean? We had some prior, and then we observed data that says that the most probable value of theta is 0.7, this one. But in our prior, the most probable value of theta is somewhere here, 0.2. When we combine this prior and our likelihood, then we see that it shifts our beliefs and it increases, for example, mostly likely value of theta to be somewhere here. It shifts it somewhere to the right because data provides such evidence. But it is not maximum likelihood estimate because prior provides some arguments against it. So we can say that prior shifts this curve to the left and likelihood shifts this curve to the right, to something in between. And this is how Bayes rule works. So here I just multiplied this curve by this curve. I have to rescale it by dividing by this value, but it doesn't matter much because I just will rescale this vertical axis. It doesn't matter. What matters is the shape of this curve, and this shape will look like shown on this picture. Are there any questions so far?
It's more or less clear.
Okay. Let us make a 10 minutes break and then continue with our studies. Now I do it.
Okay.
So just for the sake of the record, we consider the following model that discussed at the lecture when we have theta that is distributed according to this law, and we have x that is selected after we selected theta, and this x is distributed according to this law. So it is just a result of one coin tossing and the probability to get 1 equals to theta that is selected on the previous step. And here is the code that implements this data generation process. And then we created a data set from this process. And then we will use this data set to find this conditional probability. And to find this conditional probability, we have to select only rows of this data set such that this condition is satisfied and find how often we get this condition satisfied out of rows that satisfy this condition. This will get me the probability that I'm interested in. So please try to do it and send me to private messages your code and your results. Probably your partial code if you do one step. So, who succeeded with this step? Mhm. So I have two answers so far. I need more. Mhm. Okay, so first we can just filter this by condition x equals to 1. Now we have only a table for which x equals to 1. And then we can find out of this table how many times we have different values of theta. For example, we can just count theta. And we see these numbers. So out of all numbers for which x equals to 1, we have 460 values for which theta equals to 0.5 and 100 values for which theta equals to 1. And then I can just consider relative value. To do so, I just have to divide each value here by their sum. So I will do it like this. I count, then I divide it like this. And you see that these relative frequencies are about 0.82 and 0.17 or 0.18. And these values are exactly, okay, not exactly, but approximately the same as the results that we discussed at the lecture. So we see from this experiment that when we do our Bayesian estimation, when we find this posterior probability of theta, we do this thing. So we select only the results for which this condition is satisfied. So this is our data. So this is the data that we observed. And we find the distribution of the parameters of our model. In this case, this parameter is theta, provided that that this condition is satisfied. So we find probabilities of our parameters that are in agreement with our data. So this is an idea of Bayesian methods. So actually, we have two main ideas. First idea is that we believe that our parameter is random variable. This is what makes Bayesian methods different with other methods like maximum likelihood estimates. In Bayesian methods, we can ask probabilistic questions about the value of parameters. So we can ask, for example, what is the probability for the parameter to be equal to something or to be inside some region. And then we have first to begin with, we have to impose some priors. And after we impose priors on these parameters, in this case, our is this thing. After that, we can look at the data and use this data to find posteriors. So to find new distribution of the values of parameters. And basically this is done like this. This is a very simple example, but it shows how this Bayesian methods work. Now probably let me show you a package that can be used to feed so-called Bayesian regressions. This is an application of Bayesian methods to regression problems. And let me try to use it. Actually, you can try to install it, but if you are on Mac OS Catalina, you will probably will meet with some problems. I will actually I spent about 2 hours before our classes to solve these problems, and finally I managed to do it. But probably if you have these problems now, I will just send you how I solved them after the classes. But you can try to install package which is called, I don't remember, just a second, I have to look. BRMS. So you can try to install it like this, and I will just start it. I hope that it will start, but probably there will be some problems with installation. Actually, this is a package that is based on another package, actually a programming language that is called STEM, and actually it uses some compiling to C++, and so so there can be some problems. This is not as straightforward as it usual, but at least let us try to do it. I will use some data set to show you some application of this Bayesian things. Mhm. So let us read this data. In this data, we have information about pitch of a voice of different persons, of different genders, in different contexts. Context can be polite or informal. And we are interested in the relation between this pitch and this context. So is it true that people tend to tell with higher pitch when they use informal speech, when they speak informally, or when they speak politely? So let me show some visualization of this data. So X context, Y pitch, color, gender, for example. We need aesthetics here. So I see this picture. So this is informal context, and this is polite context. And we see differences between genders, and we see differences between contexts. And I want to compare these differences. And I want to do something like t-test, but in Bayesian settings. And to do so, let me try to use this BRM function. So I begin with just a simple regression, pitch, and let us assume that I have effects of context and effects of gender. Now it will try to compile this model into some C++ code and then use stan to run everything. But while it is processing, let me tell you a bit about this model. So as usually, we consider the following model, like pitch equals to beta naught plus beta 1 times some dummy variable for context. So we will encode this context as zeros and ones. And we also have some coefficient times the gender. Again, we encode this gender as zeros and ones. So this regression actually just like an ordinary regression that we already considered many times. Okay, let us look at the results. The idea for this regression, what is different in this Bayesian approach, is that parameters of our linear model, I mean these values of betas, are also considered to be random variables. So in the usual settings, we just say that these betas are just some fixed number that are unknown to us, but they are something fixed. But now we believe that they are random. So we have some procedure, just like we had here, some two-step data generation procedure. When we generated first parameters of our model, then we generated our actual data. And the same thing holds here. We believe that we initially generate these betas. We get them from some prior distribution. And then after we generated them, we generate our actual data. And we believe that our data were obtained using this process. And what we are trying to do now is to find the posterior distribution for these betas. Again, we can do it just like we did it here. Here we found the posterior distribution of the parameter theta. Actually, this is our posterior distribution. And here we find, using special algorithms, some posterior distribution for these values, these parameters of our model. And now our model converged to something, and we can look at it. Actually, we can even find of values, posterior distribution. So I will return to this summary after we investigate this posterior distribution. So I want posterior samples of my model. Let us look at this table. So these are our posteriors. So this is actually like this table can be seen as obtained in the following way. We had this model. We had this model. Then we generated randomly these beta zeros, beta ones, and beta twos. And we used these values of betas to find these values of pitch. And we did it a lot of times. And then we selected only those values of betas for which the data that we created in this way coincide with our data. This is some simplification of the process that is actually used, but theoretically, it is the process that we want to consider. So, in a sense, we say that these betas are random variables. We found their posterior distribution, and we created some sample from this posterior distribution. Let us consider, for example, this parameter B context pole. Let us return to our model. So we have actually context pole, so context polite, and this is this thing is called beta context pole. What is the interpretation of this coefficient? How can you interpret this coefficient? For example, if it is if it equals to 10, what does it mean? If we consider this model, if we believe in this model, how can you interpret this coefficient? how do you interpret, just in a simple linear model, how do you interpret the value of coefficient? Like this coefficient in this kind of regression. Mhm. Yes, this is correct. So if it occurs that this coefficient beta context pole is 10, then it means that we have a difference between two contexts. So if the value of this variable is 0, so it means that context is informal, that this condition is violated. Then, okay, let me write it down. If, for example, is equals to 0, then pitch for informal context will be larger by 10 points. No, for polite context, than for informal context. For equal gender. So I can say that, let me show that this is true. If this variable is 10, then it means that our formula is like beta naught plus 10 this dummy variable plus beta 2 times the gender. If we consider two observations for which only context is different, and then their difference in pitch equals to 10. Because if gender is the same for these two observations, then this part is the same, this part is the same, and the only thing that is different is this part. And in this part, for one observation, we have here 1, and so we have this value 10. And for another observation, we have here 0, and we don't have this 10. So this is the only difference. Is that clear?
Yes.
It is clear, at least for one student. Is it clear for
Yes, yes.
more than one student? Okay, it is clear for more than one student. Okay, well, then probably we can proceed. Then let us return here. If we believe that there is difference between two contexts, what should we expect from these variables? If we believe that there is difference between two contexts, what will we expect from these variables? So these betas corresponds to betas that are used in my regression. Especially this beta context pole is exactly the same thing as we had in my regression. we had here. So what will we expect if we have difference?
That there would be a difference in pitch.
Yes, but if we have this difference in pitch, how can we interpret it in terms of this variable? What we expect to see as the possible values of this variable? In fact, as we discussed, this variable represents the difference in pitch between two contexts, polite and informal. So if we believe that this difference exists, it means that these numbers are, what can you say about these numbers?
Close to zero.
Close to zero. If they are close to zero, then that you have difference or you don't have difference.
If they're close to zero, then there is less difference. But if they are bigger, then there is much difference between them.
Yes, so if we have some difference, then we expect that these numbers are non-zero. Let us draw the sample of these numbers. So I will use ggplot. Give histogram. So we see this histogram. This is actual posterior distribution of my values beta. And we see that for these values, it is possible for them to be zero, but the probability for them to equal to zero is rather small. Actually, we can find this probability just by finding how often we see positive values. So I can just for example, I can add new variable that measures how often we have this condition, and then I can count so we see that out of all observations that we have here, we have only 39 values that are positive. So I can find relative frequencies. So we see that for this B context pole, probability to be positive is so small. So we have 99% probability that the value of this B context pole is negative. So probably we can conclude that the actual B context pole is more likely to be negative. And this is how can we interpret this posterior. This is one of possible way to interpret it. Actually, you can extract a lot of information from this posterior. You can extract different kinds of point estimates from this posterior. But I think that we don't have too much time to discuss it in details. So are there any questions so far? Actually, I expect one question. We discussed Bayesian methods, and we started the discussion of Bayesian methods that we assume that our parameters of our model is some random variable. And then we discussed that we use our data to find posteriors. But in this story that we discussed here, it seems that we are missing one important step of Bayesian inference. Which step? You can return to the beginning of our discussion of Bayesian methods. So we have data, we have posterior. We have data in our experiment. So we have this polite data. So we assume that we obtained them in some way. But there is a part of the story that we are missing, at least when we just run this formula. So how?
How can we get a prior for this kind of data?
Yeah, exactly. Actually, prior is not something that is related to data. Prior is something that is related to model, to the parameters of the model. And in this case, we impose some prior to these variables, to these betas. And in fact, there are some default priors that are used here, and they are so-called uninformative priors. So this is like every possible value is equally likely from the point of view of this prior. But if we want, we can impose some other priors to our values. For example, let me try to use to impose some prior. So you see that with default prior, which is uninformative, we have this distribution of beta context pole. Now let us impose some prior just to see how it works. I want to do fit with prior, and I have to specify this prior. Assume that my prior is that all betas are distributed with normal distribution. For example, with 0 mean and variance 5. And I have to put some magic here, class B. And I think it should work now. Let us try. No? Mm. It used to work previously. It should be normal, not n, not just n. Okay, now it works. No? Building our package. I don't want to build our package. Why does it ask me to build something? Okay, I hope it will work now. Before we have the result, how do you think? What is the effect? I used as my prior normal distribution with expected value 0 and variance 5. So my prior is something like this. Let me draw. My prior is, oops. Something, no. Something like this. How do you think? How my posterior will change when I impose this prior? So in other sense, my prior says that it is highly unlikely to see betas somewhere here. It is much more likely for them to be somewhere here, near 0. How it will change the posterior? Yes, it will most probably shift posterior to the right. Let us look. Is it true or not? It is compiling. It takes some time. Okay. Now it works. So we have some results. Let us look at the results. I will use posterior samples, and I will use the same code to draw the histogram. Fit with prior. Okay, we see that with this prior, indeed, the graph is shifted a little bit to the right. Previously, it was like this, from -40 to 0, and now it is from -15 to 10. So indeed, the choice of this prior, the prior that puts larger weights on the value near 0, shifts our posterior to the right. So if we impose this prior, it means that we believe we impose some belief that this value of this parameter is close to 0, then we get the result that is more in agreement with this prior, of course. But it is not coincide with this prior. Again, according to the data, we have some shift to this negative region. But if we impose a strict prior, then we have less significant effect than with this uninformative prior. So this is again the feature of these Bayesian methods. So basically, this can be seen as a kind of disadvantage of Bayesian methods, that you have to impose some prior, and it is not very clear where to get them. If we think about a person that can produce two different realizations of a word, we can think about some other study from which these priors can be found just by analyzing data on different informants. But sometimes it is not very easy to find these priors. Anyway, it is very useful to think about your data as a result of application of some probabilistic models. And Bayesian models are interesting and sometimes useful concept that you can think about. I think that that's all that I wanted to tell you today. Are there any questions?
So that was the last lecture, yes?
Yes, that's correct. Today is the last classes. After that, we will probably arrange some consultations to discuss your projects.
So you will write about these hours? Or...
Yes, sure.
Thank you.
Are there more questions? Actually, my main point here is that every models, every methods that we discussed so far, they are just a tiny bit of the models that you can consider. And if you will think about your data in probabilistic terms, then you can model your data in a way that is appropriate to the data generation process that you are studying. And this is the best way to deal with these statistical problems. But to do it, you have to think in probabilistic terms. And this is this gives you much more freedom. So any questions? Okay, if there are no questions, then I think that we can stop today. And thank you for your attention.
Thank you. Bye.
Thank you.
Bye.
Bye. Bye-bye.
Bye.